Okay, this is section 1.3 from the text, also with a skosh of 1.6 at the end. So 1.3 is homogeneous equations. These notes are posted on Canvas for you to look at. And then later on Tuesday of next week, I'll actually assign some homework on this section. So 1.3, homogeneous equations. Homogeneous is a word that comes from the Greek. Homo for the same, genius is type, same type. A system of linear equations is homogeneous if all constants are zero. They're all the same type. So here's a real trivial example. X plus y equals 0, x minus y equals 0. The solution's right there, but think about it for a second. Two numbers that add up to 0 and they're the same number. They have to be 0. That's the only solution there is. Here's a quick fact about homogeneous equation, which you may remember from 3 years ago. If I have a set of homogeneous equations, if I set all the variables equal to 0, I've got a solution. So I always have a solution to homogeneous equations. Homogeneous equations, or a system of homogeneous equations, is always consistent, with one solution always being make all the variables 0. We'll call that the trivial solution because it's always there and it's not particularly interesting. We are actually interested oftentimes in non-trivial solutions, and we'll spend the rest of our time talking about that. Here's a new system. X plus 3y plus z is 0. Negative 2x minus y plus 3z is 0. Sure, again, I can make all my variables 0. Do I have non-trivial solutions? Well, theorem 1.2.2, which we covered in the previous section, says if you have more variables than equations and you have a consistent system, then you have infinite solutions. All right. Well, I have a consistent system. I already have one solution, the trivial solution. So this tells me now that I have infinite more solutions. All right. Adding those thoughts together gives us theorem 1.3.1, which I haven't written down here, but that's basically the same thing, is that if I have homogeneous equations with more variables than equations, then I have infinite solutions. All right, so I can take this system here, go down this new example, and make the augmented matrix. And let's go ahead and solve. And we had to do this here by hand, just for the sake of refreshing our memory still about how to do this by hand. I have my leading 1 already. I rigged it that way, but let's put a 0 below it. So 2 row 1 plus row 2 goes to row 2, gives me that row. I need a new leading 1 where this first 5 is. Let's divide everything by 5. And now I have this in row echelon form. Now I need to put the zeros above my leading 1 here. This is the backward steps, the back substitution. So the operation that does that is negative 3 row 2 plus row 1 goes to row 1, and I get this. All right, so that's in reduced row echelon form. Let's interpret this result properly. X minus, this first equation gives me x minus 2z equals 0. The second equation gives me x, or y plus z equals 0. I can solve for x and y. X is 2z, y is negative z, z is free. And then we'll call it, or write this in that parametric form, letting z be my parameter. X is 2 times the parameter, y is the opposite of the parameter, negative 2. All right, that's my solution. Pretty straightforward. It's what we did in the previous section, except for all the constants now are always just 0. All right. So now a new thought that ties into this, it's all part of this section, is this idea of a linear combination of vectors. You may recall from 103 or other things that you've done in math that a vector is just a matrix of one column. So here's a vector, there's a vector, just a matrix of one column. If I have two vectors with the same number of entries, that's incredibly important, then I can add them. You just add them component-wise. X plus y is 1 plus 7, and 0 plus 1, and negative 2 plus 2. Get this new vector here. Pretty straightforward. I can multiply my vector by a constant, some sort of scalar. And in this case, I can multiply by a 0 scalar if I want to. It's possible you just get the 0 vector back. If two vectors are different sizes, then I can't add them together. It just doesn't work. All right, so here's a new problem. Now that I have this idea of combining vectors together, what if I have these three vectors? V1 is this, V2 is this, V3 is this. Oh, and by the way, in class, in my notes, whatnot, I will write vectors with a variable with a line over top, an arrow over top, I should say. The textbook uses a boldface font for vectors. It's very common, except I don't do that because I can't write boldface. So, all right. So, what I want to do with this problem is I want to solve x times v1 plus y times v2 plus z times v3 equals the 0 vector, i.e. this is an equal sign here, equals 0, 0. So I want to be able to add up these scalars of these three vectors and get the 0 vector back. Well, to solve this problem, let's just expand what this left-hand side is. X times v1 is x times v1. This is y times v2. This is z times v3, and still the 0 vector over here. Continuing to expand, let's distribute these variables across the vectors, and I get x negative 2x, 3y negative y, so forth. And then on the left-hand side, I have a sum of vectors. I can add them together, and I get this. And then it stands to reason, and the book has this written down somewhere, but if these two vectors are the same, then this first entry must be 0, and this second entry must be 0. So I have now this new system of equations. That's the same system of equations that we did, a little bit above. So why do we go all through this? What's the point of all this? So what the point is that equations involving linear combinations of vectors are just systems of linear equations where the columns of the augmented matrix are the vectors. So my columns here are 1, -2, -3. So try this again. 1, -2, 3, -1, 1, 3. If I scroll up here, those are specifically the columns of my matrix there, the coefficients of that, within the augmented with the 0 part. All right. So the idea is later on, we're going to make huge use of this. The vectors are going to be incredibly important. Linear combinations of vectors are going to be incredibly important. And we just turn those into the columns of an augmented matrix and then hit RREF and interpret the result. That's going to be super important. So now let's consider a homogeneous system of equations with the coefficient matrix A, and these are just a bunch of coefficients. All right. So since I have 4 columns, that's going to relate to 4 variables, which we'll call x1, x2, x3, and x4. So how do I solve this? Well, again, I form the augmented matrix, augment 0, and put it in reduced echelon form. I use my calculator for this just to save time. And I get this result. All right, now the next task is let's interpret this result. Again, so often we're going to form an augmented matrix, put it in reduced echelon form, and now interpret the result. So first row tells me that x1 plus x3 plus 2x4 equals 0. Next row tells me x2 minus x3 plus 3x4 is equal to 0. Solving for x1 and x2, they are the ones that correspond to leading ones. That's why I'm solving for them. x1 is this, x2 is this, and it means x3 and x4 are free. And now we'll put this in a parametric form. It's easier to start off writing out what parameters are. We'll call x3s, x4t, and then x1 now is just negative s minus 2t, and so forth. Right. So that's relatively straightforward. We did these examples kind of like last time in class 2. Only difference really is that we're specifically making all the constants 0, but now we're going to take it one step further. This part is new to us here. Not abundantly clear at the moment why I want to do this, but let's just go ahead and make a vector of my variables. So the vector x has components x1, x2, x3, x4. Those are my variables. And in many ways, whenever you have information that you want to store, writing it as a vector is a pretty handy thing. Just a unit of the things I want to write out. All right. So I can do that. But above here, I said x1 is negative s minus 2t. So I'm going to rewrite x1 as negative s minus 2t. I said x2 is s minus 3t. So I'm going to write that. And x3 and x4 are just the parameters s and t respectively. So I write those in there. And now thinking about that linear combination algebra thing that I did before, I can now pull this vector apart where I have s stuff here and t stuff here. So I'm doing the opposite of combining vectors. I'm actually kind of pulling them apart. Stare at that for a second and see what happened. This all has an S term in it, so I can factor that out and write this as S times -1, 1, 1, 0. We factor the T out of this and call this T times -2, -3, 0, 1. All right, now this part's important. It says that each of these two vectors are what's called particular solutions to the system. So in specifically, i.e., this first vector says x1 is -1, x2 is 1, x3 is 0. Sorry, x3 is 1 and x4 is 0. Right, I've written that here. That's a solution. If I go back up to my augmented matrix here and think about this whole equation here, if I make this coefficient, or if I make this variable -1, 1, 1, 0, if I multiply that out and add it up, I do get 0. You can check that for every one of these equations. That is one particular solution. This is also a particular solution. Those two solutions are actually important. We're going to give them a name because they are important. And each of these two solutions, we'll call them basic solutions. Right? Kind of ties into they're specifically written as vectors right now. This would be important vectors. The idea is those solutions that are associated with each of these parameters are important. And then we're going to end here with an important theorem. So let's let A be an M by N matrix with rank A is R. As we talked about before, rank A, remember, that's the number of leading ones in the reduced echelon form. So this matrix up here, coefficient matrix, had 3 rows, 4 columns. It had rank 2 because I had 2 leading ones. All right. So back to my theorem. Let A be an M by N matrix. M is number of rows, N is number of columns with rank R. And consider the homogeneous equations where A is the coefficient matrix. This is what we did above. We had a coefficient matrix and I augmented with zeros. Okay. Result number 1, the system has N minus R basic solutions, 1 for each parameter. Okay. So wherever I have a leading 1, I don't have a parameter. When I don't have a leading 1, I do have a parameter. When I have N columns and R leading 1s, that means I have N minus R parameters left over, and that gives me that many basic solutions. If every column has a leading 1 in it, an RREF, if the rank of the matrix is equal to the number of columns, then I have no basic solutions. And the only solution I do have is the trivial solution. I want to ponder that for a little bit. And then the other part here is super important, and it's not going to kick in probably yet, like how important this is. We'll end up using terminology downstream that will illuminate what's really going on here. But every solution can be written as a combination of these basic solutions. Okay. So going back up to this example here, I wanted to solve this system of linear equations, and I was able to write out solutions as basically a combination of these two things. If I were to get numbers for S and numbers for T, I could add these together and I get a new solution. And it turns out that I can get every solution by doing this process. And that's really, really important. Every solution is a linear combination or a combination of these two basic solutions. So that leads us out of 1.3. All right, we've covered everything we needed to cover in section 1.3, and I'll give you some homework for that later on. All right, real quick, I'm going to show you something in section 1.6. What we've really been doing in chapter 1 is just reviewing linear equations. In sections 1.4, 1.5, and 1.6 are all application sections. They were interesting. 1.4 is about network flow, about, if you have, let's say, cars on the road grids, and you have a certain number of cars coming in, a certain number of cars coming out. You can do a lot of linear equations to figure out how cars transfer on there. 1.5 is about circuits. If you know things about resistance and voltage, you can figure out certain things about circuits. I find that really interesting. I like electronics personally. I'm not keen on teaching you enough electronics and reading electronic diagrams so that you can answer the questions. But if you are a physics major or ECE major or just curious for this kind of stuff, then go for it. It's just basically understanding a circuit can amount to a system of linear equations. The one that I'm going to work on for just a second here is applications to chemical reactions. This is also an interesting thing. It's an important part of chemistry, and the math behind it is simply linear equations. All right, so here's the idea is I can take hydrogen molecules and add them to oxygen molecules and get water molecules. Right? Pretty simple. The truth is, matter can't be created or destroyed. These atoms are what they are. And so I can't just take one hydrogen molecule and add it to one oxygen molecule and get one water molecule, because I had two oxygens here. I've lost an oxygen. So what happens is I have a little system. I need two hydrogens for every oxygen, and then I'll get two waters. All right. So over here, I have a total of 4 hydrogens, and then I have 4 hydrogens. I have 2 oxygens, and over here I have 2 oxygens. They call this a balanced equation. So part of a chemical process analysis is coming up with balanced equations. Let's balance the following reaction by, if you burn octane in oxygen, well, then here's the oxygen added to, or sorry, here's the octane added to some oxygen. When you burn it and these chemicals react with each other, you get carbon dioxide and water. So the question is, how much octane and oxygen do I need to produce how much carbon dioxide and oxygen or water? How do these chemical reactions balance? So how much octane is X, how much oxygen is Y, how much carbon dioxide that comes out is Z, and how much water comes out is W. Those are my variables. Right? So now if I just equate the number of carbons on each side and so forth, I can get a bunch of equations. There are 8 carbons on this side. There are Z carbons on this side. So 8X equals Z. And then you can keep on working through this. How many hydrogens on the left-hand side? There are 18X hydrogens. On this side, there are 2W hydrogens. Let me set this up. You get this real quick system of equations. The text here, where they talk about it, does some reasoning, which is fine, but just put this in your calculator and hit RREF and you'll get a solution. When you get a solution, it'll have some nasty looking fractions in it. Possibly use your calculator to do that thing where you can convert your solution to fractions. And I think I did that actually in my calculator. It's just going to show up well. Bam. All right, so you get this fraction, right? The important part, though, is that you don't really want fractions of molecules. I'm not sure you can have a fraction of a molecule. So a key portion of this is that we have this new constraint. My solution has to be positive integers. I can't have negative waters somewhere in my system, whatever. So you end up multiplying everything through by 9 to get integers. And then one solution that you can possibly get is 2 octanes and 25 oxygens give you 16 carbon dioxides and 18 waters. And then from there on, you can build up. And if I have, a lot more of this kind of stuff, I get a lot more of that kind of stuff. So this balance is kind of an interesting thing. All right, that covers it for this video for Thursday's lecture. As always, if you have questions, send me an email and I'll do what I can to help you out.